Okay, so this is geometric proofs using vectors part 2. I want you to read that question and read it and read it and read it until you understand it, understand what it's asking. You'll have to draw a picture if you're going to understand it, I think. Hopefully, if you've thought about it, you've drawn a picture, you understand what the question's asking. Prove the sum of the squares of the lengths of a parallelogram's diagonals is equal to the sum of the squares of the length of the sides. So, what does that look like? Here is a parallelogram. Now, the sum of the squares of the diagonals. So, that is a square drawn off that diagonal. In other words, take the diagonal, square the number, and you'll have the area of that square. This is a square drawn off the other diagonal. If I look at both squares at the same time, and I add those areas of those squares together, poly 5 plus poly 6, I'll get 211.41. That's the sum of the two diagonals squared. The other bit is poly 4, poly 3, poly 2, poly 1. The sum of the four squares of the lengths. So length squared, length squared, length squared, length squared. That is also 211.41. So we're trying to prove that these four squares is equal to those two squares. Okay, let's do it. Obviously, if you try to do something like this without drawing a picture, you're a bit silly. Here's our parallelogram with two diagonals. Now, we let OA, vector OA, equal vector CB because they're parallel, they're the same length. And we'll just call that vector A. I'll just draw it on my image itself. So that's vector A. And we can let OC equal AB, same magnitude, same length, same direction. And we'll call that vector C. All right, so we've got an A, a C, and a C. And similar to our previous proofs, we can now say that vector OB is equal to A plus C. OB is equal to A plus C. And vector AC, it's a little more complicated. It's negative A plus C, or C minus A. All right, so nothing new there. We're just sort of setting the scene for our two diagonals. Parts of this are going to feel a little bit familiar. We're going to take vector OB, that's the diagonal there, and we're going to square it. Now that's going to be equal to OB dot OB, because that's the dot product, and squaring our dot product gives us that. Now we know that OB is equal to A plus C. So we have this situation, which we've seen before. A plus C, dot product, A plus C. Already learnt that the dot product is distributive, so we can say that A dot A plus A dot C plus A dot C, so that'll be 2 A dot C plus C dot C. Need to be careful about that 2 A dot C. It's two lots of A dot C plus C dot C. So A dot A is the is equal to the magnitude of A squared, and then we've got this thing again, 2A dot C plus the magnitude of C squared. Stop for a minute, think about what we've done. We've said that vector OB squared is equal to the magnitude of A plus the magnitude of C plus A dot C times 2. Only one of the diagonals. What about the other diagonal? Let's do that one. A very similar story for the other diagonal, AC squared. That's going to be AC dot AC. But remember that in the beginning we said that AC is equal to C minus A. So now we have C minus A dot product C minus A, which is going to be A squared minus 2AC plus C squared. Now, that's pretty good. You can see they look pretty similar. It's just that the length of AC, it's obviously shorter than the length of OB, and so the square is going to be smaller. That's why we've got a negative 2AC rather than a positive 2AC. We're trying to prove the sum of the diagonals is equal to the sum of the outside lengths. So let's sum these two diagonals. Sum of diagonals Now, what is the sum of the diagonals going to be? Well, it's going to be OB squared plus AC squared, which is going to be magnitude of A squared plus 2AC, A dot C, plus C squared plus A squared minus 2A dot C plus magnitude of C squared. All right, so what happens? We've got a 2AC, we've got a negative 2AC, we can cancel those out, and we're left with magnitude of A squared plus, there's another magnitude of A squared, plus a magnitude of C squared, plus a magnitude of C squared. All right, that's our proof, because take a look. I'm saying the sum of the diagonals is equal to all of this, which is equal to A squared plus A squared plus C squared plus C squared. The sum of the diagonals is equal to the sum of the squares of the sides. I should say the sum of the diagonals squared. I should say the sum of the sides squared. And there's our neat little proof. It kind of pops out of nowhere. I like that one. That brings us to vector proof 4, and it's going to be something you've seen before. Prove an angle in a semicircle is a right angle. So you've done this before, but not with vectors. We're going to do it with vectors this time. So we're going to prove that that is a right angle. You might want to pause the video here, seeing that you've already done 3 vector proofs. You might want to consider some of these, or the ways in which you can do it. A little hint, I'm going to draw in another little line here from OB. All right, so I'm going to make some vectors here. Let's get started. All right, so from the get-go, I can say one thing for certain. The magnitude of vector OA is equal to the magnitude of vector OB, which is equal to the magnitude of vector OC, because they're all radiuses. Now, they're not equal vectors. It's just their magnitudes that are equal. Important. So this next little bit is just labeling things up. Let vector OA equal A. Let vector OB equal B. Let vector OC equal C. And all of those vectors are obviously OA, OB, OC, so they're all moving in that direction. And now it's important to understand the relationship between vector C and vector A. Vector C equals negative vector A because they're the same magnitude and they're going in exactly opposite directions. One's going that way, one's going west, one's going east. So negative vector C equals negative A. Now I'm going to do the dot product of vector BA and the dot product between vector BA and BC. And right angles, dot products. If you're looking at right angles and vectors, you're talking about dot products. So we're going to say that vector BA dot product vector BC. Okay, and now we need to consider what that vector is. Vector BA is vector A minus vector B, and then we're going to do the dot product of vector C negative B. You can pause the video and think about why BC is C minus B, but the important thing to note here is I don't want to talk in terms of these 3 vectors because I now know that C is actually negative A. All right, so you can think about where to go next, but it shouldn't be a surprise because in the previous 2, when we've gotten to a stage where we've got 2 vectors, dot product 2 more vectors, we can use the distributive law, negative A dot B, negative A dot A plus B dot B plus A dot B. So the negative A dot B and the positive A dot B are going to cancel each other out. The negative A dot A plus B dot B. So B dot B is the magnitude of B squared minus the magnitude of A squared. So what do we know about the magnitude of B and the magnitude of A? B is this thing here, A is this thing here. Their magnitudes are equal, right? So we can just say that they both have magnitudes. We can choose whatever we want. We can say they've both got magnitudes of OA. So OA squared minus OA squared. What's that going to equal? Well, that's going to equal 0, right? Same magnitude squared. Subtract one from the other, you get 0. So we found the dot product. The dot product is equal. Therefore, right angle between those vectors. And what do those vectors happen to be? They were BA and BC. If there's a right angle, then we've just proven an angle in a semicircle is a right angle. There were vectors, vector proofs 3, this one, which was a bit cumbersome, but we got there. And then this one, which is just a novel way of proving something we already knew how to prove, just did it using vectors. You can see that in the second, third, and fourth proofs, the same kind of things kept happening. We were talking about right angles, and then we could use that property of the distributive product, dot product, to work with things there. You could be asked any of these proofs, and you should be able to reproduce these proofs yourself.